Hey everyone, welcome to the very first video on Nocturnal Coder, a channel where we break down complex AI and machine learning topics into short practical lessons. I'm Harsh Bhargav, and in this first video we are going to learn PyTorch in just 30 minutes. From tensors and Autograd all the way to training and evaluating a neural network right inside Google Colab. I've built this tutorial to avoid early mistakes I made when I first started, so you can focus on what actually matters. And even if you already know the concepts, this will be a great refresher before you jump back into deep learning. So if you're ready to learn fast and code smarter, make sure to subscribe and let's dive right in. So let us start by understanding what tensors are first. So a tensor is a multi-dimensional array that stores numerical values. So let us start by first importing torch and numpy as np. I will start by creating these three tensors with the shape of 2, 3, 5. The first tensor will contain random values. The other two will contain all ones and all zeros. So let's execute, and we can see our first random tensor has 5 values in the first matrix, and then there is a stack of three such matrices, and then there are two stacks of such 3x5 matrices. And similarly, we have our ones tensor and zeros tensor with all ones and zeros. Next, we're gonna see how we can actually convert the tensors to numpy arrays. So for this, I'll define my t tensor with all ones, and then I'll just use t.numpy to convert it into a numpy array. If I run this, I get a tensor with all ones and then a numpy array. Uh, we can also do the reverse by first defining a numpy array and then getting a tensor out of it using from numpy, and you can see that from this numpy array I'm able to get this tensor with the data type of torch.float64. Next, we are gonna talk about performing some operations on these tensors. We're gonna see two types of multiplications. So first we start by defining these two custom tensors. The first type of multiplication that we're gonna see is called an element wise multiplication. We're gonna use a star for this, so a star b, or we can also use this torch.mul a comma b. So let's print it out and see. So we get this new tensor, and this we get by multiplying the corresponding elements. So 1 into 5 will give you 5, 2 into 6 will give you 12, and so on. Next, we'll look at matrix multiplication. Uh, so let's execute this, and we see that we get matrix multiplication. So 1 into 5 plus 2 into 7, so 5 plus 14 will give you 19. And similarly, you can go on. Now, this is something important to understand. We can actually transfer our tensors to GPU if it is available, and we can do the computation in the GPU. This will make our computations much more faster. So I'll show you. If I go to runtime, if I go to runtime, if I go to change runtime type, you can see T4 GPU is enabled for me in this Colab notebook. That means I have a GPU available. What I can do is I'll run this condition first if torch.cuda is available, and if it is, then I'll create a copy of this B tensor in my GPU. So remember this, here I am just creating a copy, so this B tensor will still remain in the CPU. So once I do this, you can see the device tensor is stored on CUDA 0. Now this is an interesting thing to understand here, is that two tensors can only be used for a computation if they are both on the same device. So for example, if I run this function, it will work out well because both a and b are on CPU. But if I try running a comma tensor, we know that tensor is in the GPU and a is in CPU, so this will give me a runtime error, and then you can see I get this runtime error, expected all tensors to be on the same device. I can also actually transfer this tensor B to GPU like this, and if I run this, then you can see now this function also fails, saying expected all tensors to be on same device.
and because we have transferred B to GPU, this won't work out as well. Okay, so now let's go to the next section and we'll talk about backpropagation now. So let me just edit this code a bit for you. Okay, so let's say we start with these two tensors, A which has a value of 5,6 and B which has a value of 2,3. What I'm doing here is I'm computing C by element wise multiplying A and B and then summing all the values. So in this case 5 into 2 will give you 10, 6 into 3 will give you 18, so 10 plus 18 will give you 28. So C should have the value of 28. If I run it, I can see C is 28. Now you would be curious and you'd be thinking that what this does, right? And this is nothing but we are asking PyTorch to actually track this variable. So if I turn requires grad to true, PyTorch will start tracking this. And how this will be helpful, we'll see in a moment. Let's say I want to find out the differential of C with respect to A, right? And this is how backpropagation works, right? It uses chain rule to sort of get the gradients so that you can update the weights and biases accordingly. So in this case, if I run this particular function or this particular method called backward, this will actually backpropagate from C and take into account all those variables where the required grad was true and then give me the grad values. So let me run this and print out the grads. So you see that a dot grad give me a value of 2 comma 3 while b dot grad is gives me none. So now this makes sense because b dot grad was not being tracked. Now let us see how this 2 comma 3 comes in for a dot grad. So as I told you in backpropagation, because I'm backpropagating from C, this this will compute del C by del A. Now del C by del A will give me B, right? Because while I'm doing partial differentiation with respect to A, B will be treated as a constant. So dc by dA will be just B, and B is 2 comma 3, you can see, which is the same as A dot grad in this case, right? What if I square it, right? If I square it, then del C by del A will become 2AB. So then A grad should be 2 into 5 into 2, which is 20, and 2 into 6 into 3, which is 36, right? So let's see if that is the case, and here it is, 20 comma 36. Now what if I also turn on the gradient tracking for B, right? If I do that, then you can see B dot grad is also being populated, and this is being populated by del C by del B. Now del C by del B here you can see would be A square, right? And A square is what? 5 into 5 25 comma 36, which is this value. Now let us take it a step further. What if this C was being used to calculate another variable Z, right? And now what I'll do is I also want to retain the gradient tracking for C. That's why I'm using this C dot retain grad. Now what I will do is I will back propagate not from C but from Z, right? Because Z is one step ahead of C. So if I do this and I print out the gradient for all of these three, we get 112, 168, 280, 336 and 56. Let's see how this thing works. So let's just see how it calculates from dz for dz by dA, right? And you'll get the idea how we get the others with this. So dz by dA from chain rule would be dz by dc, because Z is totally dependent on C, and then we multiply this by dc by dA, right? And this will give me 2C, right, multiplied by dc by dA will be B, which from here we know that the value of C is 28. So this will be 2 into 28, which is 56, multiplied by B which is has a tensor value of 2 comma 3, right? And then if you do this computation, this will come out to be 112 comma 168, which is what we have here, right? So you can see how powerful this backward method actually is. This is actually using Autograd to do the whole back propagation and filling in the grad values, which can be used to further modify the weights. So let us now use all of our learnings so far and try to sort of come up with a simple linear regression model. And what we'll do here is we'll create the data on our own. So we start by creating x values as equally spaced numbers from 0 to 100, and we'll have 100 such numbers. So let's see how it looks like. And I actually want to introduce you to this concept of unsqueeze and why we use it, and I'll do it now. Let us first look at how x looks like without unsqueeze. And if I do this, you can see it creates 100 values from 0 to 10, which are equally spaced. Now, for linear regression, the y pred looks like this. So I have to matrix multiply x with w. Now the weight is initialized as a 1 cross 1 matrix, and I can't just use this 100 shaped matrix for this multiplication, right? So to multiply with a 1 cross 1 matrix, this should be a 100 cross 1 matrix. So I have to introduce an additional dimension to this tensor basically, and unsqueeze it is what I use to do this. So whatever index you write here in unsqueeze, an additional dimension will be inserted in that particular index value. For example, if it is 0, then I'll get a 1 cross 100 tensor, right? If it is 1, then I'll get a 100 cross 1 tensor. If this is minus 1, it will just add at the end of the tensor. So this time we have 100, so it will be 100 cross 1 again. So let us run it for squeeze 1 and then see how it looks like. And there you go. You see we get this column sort of a thing, and if I go down, you can see the shape now becomes 100 comma 1, 100 cross 1. So I can now go ahead with the matrix multiplication. I'll just quickly show you. If it was 0, how will it look like? So if it was 0, then we get 1 cross 100 matrix. So this is an important sort of method to remember. So now let's go ahead. Once we come up with this x, what we're gonna do is we are gonna come up with our y. So we are actually using this particular equation to come up with our y. So we'll have 2x plus 1, and then we'll add some Gaussian noise to it. So 2x plus 1, and this is we are adding some Gaussian noise to it. Next, what we will do is we'll initialize our weight as a 1 cross 1 tensor, and we'll turn on the gradient tracking because weights has to be changed, and the same thing for bias, right? I initiate my bias with the value of 0, and just to give you a glimpse, okay, yep, this is how it looks like. So I have a random weight initialization of 0.295, and then the b tensor is 0, and this is 1 cross 1. So when I run it, I'll get again a random weight assigned, and but the value of b will be 0 because torch.zeros is being used, and both of them are being gradient tracked. Next is my learning rate. So I'm using a learning rate of 0.01 here. After this, I'm gonna run my for loop for the training purposes. I'm gonna run for 500 epochs. Now let's start with the forward pass. So the forward pass will be kind of easy, or this computation will be kind of easy because it's just x into w plus b, and then we just calculate our loss. this this loss is a MSE loss, mean squared error. An easy way to remember how you write MSE is you go the reverse way. So first you write the error. Error is nothing but the difference between the prediction and the target. Then S for square, you square the error you found, and then you take the mean of it. That's how you get MSE. So next, what we're gonna do is we're gonna back propagate. We're gonna use backward, and we are doing this to because this is like a very simplistic structure. This will just give me the differential of with respect to W and with respect to B for loss. So del loss by del W and del loss by del B is what I get. And using those, I can use this gradient descent to sort of update the W's and the B's. I'm using this condition, torch dot no grad, uh, because I don't want to gradient track these two. I don't want any sort of computation on these. These are just for updating the weights and biases. That's why I'm using this particular condition. Next, once the update has been made, what I will do is I will turn the gradients wherever the gradients are being stored to 0, because if I don't do it if I run this again, this epoch again, the this will start accumulating, right? So I have to clean it out. So to clean it out, I'll set them to 0 again after the loop has taken place, and I just print the loss after every 100 epochs, and at the end we'll see what is the learned W and B values, and they should come out to be near 2 and 1, as we know the equation that we are using in the first place is 2x plus 1 and then some Gaussian noise. So let's see how it works out. And you can see the loss is gradually decreasing. Also the learned value of W and B are really good. So you got 2.01 and this is also near to 1. I mean, if I run it again, I'll get probably something much better. So yeah, so this is how you can write basically a linear regression using all that we have learned so far. But now let's go ahead and look at neural networks and how you can come up with those, because that is the main aim of this tutorial. So what I'm gonna do is I'm gonna start with some basic imports, and I'm gonna tell you how to use, like, why I'm using these imports. But there are some imports that are relevant to Torch, and then there are some from sklearns. The ones from sklearns I am just using to load the dataset that we are going to use. So we're going to use basically we're going to use the iris dataset for this exercise, and the iris dataset is nothing but a classical dataset for machine learning. It contains about 150 records of iris flowers from 3 different species, so it's kind of a categorical data. And feature wise, it includes 4 different features. It contains sepal length, sepal width, petal length, and petal width. So, and then we're gonna actually use this to classify this neural network to classify this data set into different buckets of species. So let's go ahead and execute this. Next, what we're going to do is we're going to do some basic pre-processing using sklearn libraries. So we load the data, we put the data the features into X, and then we put the target into Y. Next, we are gonna use this scalar and fit transform, and they're gonna do a very simple operation where they're gonna replace these X values with their corresponding Z scores. This is basically done so that all features are on the same scale and the model treats them equally. Also, it makes the training more stable. So this is something that is like really standard uh, practice. Next, what we're gonna do is we're gonna use this train test split to create a 20% test and 80% train dataset split. Now this is really important. So now, as we have already learned that PyTorch deals in tensors, it is important to convert these splitted datasets into tensors. So we're gonna just do torch dot tensor, and then given the corresponding dataset along with the data type we want it to be. Now we're gonna use this data loader that we had imported early on here, and the reason we're going to use it is to create batches. So we know that there were like 150 records, so 80% of those are in train, so those are like 120. So we are not going to push like all 120 at once in the while training, but we're going to create batches of 16, and we're also going to shuffle the data. So I'll just show you how the data basically looks like, and this is basically before data loader, so there's no shuffle in this. Okay, so oh, I forgot to run this, so let me run this and run this. Okay, so these are like the four feature values after after being converted to their Z scores, and this is what Y looks like. It has three different categories: 0, 1 and 2. Okay, so now let's go ahead and start defining our neural network. So this is basically how you always start with your neural network. You start by defining a class, and that class always inherits from this parent class called nn.module, and this is like really helpful, and you'll see why in a moment. First you start defining the init function, and you'll do this. You'll call the parent constructor first, super.init. You start creating, so for this particular data set, we are going to create a simple neural network which has one input layer, one hidden layer, and one output layer. So we will have a structure where we have four nodes in the input layer, eight in the hidden layer, and three in the output layer. Four nodes in the input layer because there are four features, eight in the hidden layer because I don't want it to overfit or underfit, so I thought eight would be sufficient enough. Three output because we have three different classes that we want to classify the data into. We start by creating this first layer, and we're going to use this nn dot linear, and it represents a fully connected layer that performs a linear transformation on the input. So this is what linear transformation actually looks like. So output is equals to x into w transpose plus b, where w is the weight, b is the basis. We have four inputs, so four, we'll put four here, and then eight in the hidden layer, eight nodes in the hidden layer, so eight here. The next layer will go from 8 to 3, so this is how we create the next layer. Next we'll write this forward function, and it is really important that you name it forward, and this is because when you call PyTorch model, its built-in call method runs automatically and then executes your forward function. That's why every network defines a forward function. After this, you're gonna come up with a activation function. So we're gonna use relu. So we'll just pass the output of the first layer to relu, and then whatever we get from here, we're gonna pass to the second layer, and then we're just gonna return that. That's it. You're done with your neural network class. Next, we'll initialize this class and call it model. Now we have to select the loss criterion. In this case, I'm going to use cross entropy loss because this is a categorization problem. This will help us get probabilities from the logits and then use those probabilities to compute loss based on the target. So this is why I'm going for the cross entropy loss in this case. For optimizer, I'll use Adam, like this is one of the most famous ones. And I just pass the model parameters here and the learning rate of 0.01. And you see that this is really interesting that you don't have to do much. Everything is being taken care of by these functions, methods that are already present in PyTorch, making your life really easy. Next, let's start with the training loop. So we're gonna go for 20 epochs. We have the train loader which contains like batches of 16. We're gonna call them one by one. We can call inputs and targets, and this is the first thing we'll do is we're gonna put all the gradients to 0 in the optimizer, as we are already seen in the last linear regression example that we saw. We'll do the same thing here. Next, what we're gonna do is we're gonna get the outputs from the model. So we'll use the model. We'll just place in the inputs that we got from the train loader and get the outputs. So you see how easy it becomes, because this class that you made is inheriting from nn.module, and everything is being taken care of by nn.module. All the gradient tracking, all the other stuff that has to be done is being taken care of nn.module. So you just have to call your model, provide the inputs, and then you get the outputs. Next, you'll put this output into the criterion, the cross entropy one we defined, to get the loss. And I'll run the backpropagation on this loss. After the backpropagation, I'll use this optimizer dot step. So earlier in the linear regression, we were actually optimizing, updating on our own using that gradient descent. But this time you can just call optimizer dot step and it'll take care of everything. And then again, we're gonna print after every 2 epochs to see the progress of the training. Next, what we're gonna do is we're gonna come up with some sort of evaluation. So we want to see how it works on the test set. And for that, what we're going to do is we're going to define this condition first. So these equations has nothing to do with any of the computation. So nothing has to be tracked here. Simply we're going to get the outputs from the model by plugging in the X train. Now out of these outputs, we just need the indices of the node that contains the maximum value. So every time the neural network will give us three values. So whichever one of them is the maximum, their index is what we called our prediction. Now I'm gonna get the accuracy by comparing this prediction with the actual target y test, and this will either give me 1 or 0, this comparison. And if I take the mean of all those ones and zeros, I will come up with my accuracy. So this is how this line works. If I multiply that accuracy by 100, I should get the test accuracy in percentage. So let me just quickly run this now and show you the results. Okay, so you can see the loss is going down, and then we are able to get like 100% test accuracy at the end. So this data set is like really not complex, and just by using a simple neural network, we are able to learn it like pretty well. I also want to touch base on one more thing. Since this is a very simple neural network, there are no if else conditions or anything complex in this. We could have actually done this without creating this class and directly using something we called sequential. So we could have just written this neural network in one line, right? Using nn.sequential. So you define the first layer, you define the activation function, you define the second layer, and that's it. You're done. So if I run this will again give me the same results, right? So this is something I wanted you to know. So now let's talk about running on GPU. So you might have noticed earlier we talked about the fact that the tensors have to be transferred to GPU, so that for the computation to take place on GPU. Right now I have not done any such thing for both the linear regression model and this neural network. We know that all this computation has taken place on CPU, even though I have my GPU enabled here. And at some point of time you would actually need to use this GPU, and this is because this data set was like really small and not that complex. But once the neural network becomes more complex, once the data set becomes really large, it is much easier to compute it on the GPUs than on CPU. So let us see how we can modify this code to actually run it on a GPU. So the first thing I'll do is I'll see if the device, like the GPU, is available. So uh, we'll call torch or device as CUDA if the GPU is available, else we'll call it CPU. So in this case we already know that the GPU is enabled, so we'll get this as CUDA. Next, what we're gonna do is we're gonna convert these tensors. Sorry, we already have converted this dataset to tensors. What we're gonna do is we're gonna transfer the test ones to the GPU directly, right? Because we're doing all the computation on GPU, so the YPRED that we come up with eventually and the model will also be transferred to GPU. So all the computation and the YPRED will come out to be on GPU. So if the test remains on CPU, then we won't be able to do that comparison for accuracy, right? So we have to transfer these X test and Y test on GPU. I'm not gonna transfer train right now, and I'll show you why. Because when I'm getting these batches from the train loaders, then I'm gonna transfer these, then I'm transferring these to the GPU. That's why I don't do it here. I do it like right here before the computation takes place. And then one more important thing, the model also has to be transferred on the GPU, right? So the model has to be transferred on the GPU, and then everything else remains the same. You do all these computations, you do all the same evaluation. And let me just run this and show you that now it is running on CUDA, and the loss is again going down like this, and I get 100% test accuracy.
So finally, I would like to talk about two modes that nn.module provide us with. And these two modes are model.train and model.eval. So you can actually write model.train here.
And your model.eval.
Before you start evaluating your model. And so this will be useful if you are sort of using techniques like dropout or batch norm. So you want the dropout to be enabled when training, but you want it to be disabled when evaluating, and these two takes care of that uh, on their own. So let us just run this again, and you can see, yep, you can see it's working. It's working fine.
So that's a wrap for today. You just learned PyTorch from the ground up, tensors, Autograd, model building, and training loops. This is Nocturnal Coder signing off for now. Keep building, and I'll see you in the next one.